Hi, and welcome to a discussion with Matthew Hagan regarding composite quantum simulations. We will be particularly focused on how to combine the frameworks of Trotterization and QDrift into one approach that you can use for different kinds of simulation problems. I hope you enjoy that.
So I guess I'll start off with one question. Do you know what a quantum circuit is?
I do.
Okay, good. Do you know what Trotter Suzuki is?
I do as well, and I think there we could actually start to go into some detail. So I spoke to a couple of people that have been looking at Trotterization before,
Uh-huh.
and I got kind of, well, high level overview of that a couple of times. Getting your perspective on it as well would be interesting so that, well, I have something to compare those views to. And then Qdrift would be even more interesting for me to get, like, well, a bit more information on.
Yeah. So you've never seen QDrift before?
I haven't seen it, no.
Okay. So that means you haven't talked to Earl yet. He's
True.
the guy who he's the guy who came up with QDrift. Um, Came out in like 2019, which for it's a fairly simple idea, and I'm surprised that, I was surprised, my advisor was surprised it took so long for somebody to sit down, do the analysis, and say, hey, like this idea works. Um, but yeah, so uh, how would you summarize Trotter in your own words?
I would say it's a method of doing, of time evolving. If you want to time evolve a Hamiltonian, it
Yep.
gives you a way of breaking that time evolution up. Not sure if it's in sequential, smaller discretized time chunks or whether you're doing it in another way, but you have some time evolution operator that you would apply, and the trotterization is a way of breaking that down into more um, manageable partial evolutions. That's how I would phrase it. Now, I don't
Exactly.
know exactly how we break that up. Like my conceptual understanding for that is not great, but that's how I would summarize it with a brief understanding I have.
Yeah, that's right on the money. Um, so the idea that I like to think of it is just think of like one single Trotter step, which is
Mhm.
where you have some time t and you want to simulate your entire Hamiltonian. So let's just say this is a like an atom or two atoms sitting next to each other. You
Mhm.
can have the electrons floating around. So you have electron electron, and you have proton electron kind of interactions, right? If you
Right.
want to simulate the entire wave function, say, of a single electron, normally you would have, electron plus electron, electron plus proton, electron plus proton.
Mhm.
What Trotter says is that if your time is small enough, you can get away with just simulating the electron proton and then doing the other electron proton and then doing electron electron. And as your time goes to zero, that error also goes to zero. And it goes to zero on the order of t squared, where t is like your little time that you're simulating for.
Mhm.
Uh,
Okay, so yeah, so assuming you do it granularly enough, the error scales down more rapidly than
exactly.
well than the break. Okay, fine.
And so kind of the beauty of this is that if you want to do for a long time, you can just view some finite time t as a bunch of really short time steps. So essentially, like if you think of one of your Hamiltonian terms as being like red, the color red, and the other one as being blue, it says that if you do a little bit of red, a little bit of blue, and then a little bit of red, a little bit of blue, it's going to look like purple.
Mhm.
And so if purple is your total Hamiltonian, it can kind of be thought of as these two constituent parts just sort of flashing and interacting back and forth.
Is there a way to get conceptually why the error scales down quadratically with the time step?
Yeah, I think you just have to do if you just do a Taylor series of
Uh-huh.
both of these two sides of this equation, you do a Taylor series and you see it goes like t squared. So the first order
Mhm.
terms cancel out.
Mhm. Okay.
Um,
Is it something like, could you think of this, like maybe this is a silly analogy, but I'm trying to think of it in terms of, let's say you have, you would simulate a gravitational system or something akin to that. So you have one planet, then you have two larger planets that would pull onto that, and you want to simulate the trajectory or something. Is it akin to doing like many partial simulations of the gravitational effect from each of those two masses on your first one? Because if you do something like that, then I guess you would get a trajectory that's somehow like also approximating the actual trajectory it would take if you simulated the full system with the complete physics, and you couldn't do it in just two steps. Like let's say you want to simulate some long time period, you couldn't do it in just two steps because, well, you would have too large of a displacement of your original mass after a certain set of time. But if you do it in rapid alteration, then you would kind of get the appropriate trajectory, at least conceptually speaking. um, do you think that's a good way of thinking about it, or?
that it seems very similar at a high level, but as far as like, the specific like T squared kind of stuff like that, I have no
Yeah.
clue. But it does seem like very similar in spirit.
Uh-huh. Okay. Okay, but cool.
Uh,
So is there anything important about trotterization beyond that that is useful to know for the purpose of the paper that you guys wrote?
um, so there is one part about it, and this was kind of only really spelled out in detail, I think in either 2018, anywhere from 2016 2019. I forget the
Mhm.
exact year, but pretty recently. And what this paper spelled out is just called a theory of Trotter error. Is they show that I mentioned that the error goes like t squared if you just do
Mhm.
like HA then HB and then HA then HB. Um, there are higher level orders. We're not going to get into that, but there are high level orders that can reduce this t squared down. But one of the biggest things is that there's a prefactor, like there's a constant factor in front of that t squared. And it depends on how strong the commutation is between the A Hamiltonian and the B Hamiltonian.
Mhm.
So if you take the commutator, which is just say HA times HB minus HB times HA,
Mhm.
that's just some matrix, and you can take a spectral norm of that. And what this paper showed is that uh, the error in a Trotter formula, it depends on this commutator for this simple order. And then for these higher order Trotter errors or Trotter formulas, it depends on these like nested commutators where you do like a commutator of a term and a commutator.
Okay. What does that represent? The commutator of a term and a commutator?
It sort of just tells you, uh, it shows up in these like uh, like uh, like Baker Campbell Hausdorff formulas. If you just go on Wikipedia, there's a Baker Campbell Hausdorff. There's a bunch of these kinds of expressions showing up, and you can think of it to where if this commutator of a matrix and a commutator, so like say a second level, if that's zero, it tells you that you only really need to consider like three interactions, so like three level interactions, or like three body interactions. Um, so it kind of tells you to the extent at which at how far the system is sort of propagating the wave function
Okay.
or the
As
interaction,
opposed
I
to
guess, between the parts.
mhm. As opposed to what? So you said you only need to take into account three body interactions. Was that what you used?
Um, sorry, could you repeat that?
And so you said if that commutator is zero, then you only have to take into account, was it three body interactions that you used?
Yeah, I'm not quite sure like specifically, but the idea
Uh-huh.
being, say if the first level commutator is zero,
Yeah.
then that tells you these two terms like really they don't really interact in a bad way. You can kind of just split them apart.
Mhm.
Uh, if it's three level, um, yeah, actually, I'm not going to say it's a three body interaction. So I would say no. It just tells you that like it's kind of not spreading too rapidly. Like the interaction isn't very tight,
Uh-huh.
or the information's not spreading very far.
Okay. Okay. And then in the context of this paper, it's relevant because we want to consider also higher order trotterization in what we'll get to. Um, how do those then play a role? So we have these commutators now, and these results, these previous results, how do they tie into the paper that you're looking into?
The whole idea behind this paper was like, let's say I give you, there's a couple different ways to approach it. The easiest way is like, let's say I give you a Hamiltonian and I tell you it's got two pieces to it, A and B. And if you were to do a Trotter step, what you would do is you say, okay, I can do e to the I ht if I just do multiplying small pieces of e to the I at or e to the IA delta t, and then e to the IB delta t. And you repeat these and you get the overall evolution. And so now the next idea is like, okay, what if I lied and I said, and you can't actually really do e to the IAT? Like A is secretly a sum of A1 plus A2 plus A3 dot dot dot, and then B is actually a sum of B1 plus B2 plus B3 dot dot dot.
Mhm.
Like now, if you had kind of already done this breaking up of H into the EIT and the EBT, could you still somehow do the actual simulation? And what we showed is that if you do the E to the IAT, let's say you do this with a trotter, you just further break it down another level,
Mhm.
right? So you
You
say,
mean you break it down so you do somehow individual evolutions of the breakdowns of that HA in this case?
yeah. So
Okay.
you have H is A plus B,
Yeah.
and then A is A1 plus A2 plus A3. You've already
Mhm.
done e to the IH as e to the IA times e to the IB. So now you're going to take e to the IA and break it down as e to the IA1 times e to the IA2 times e to the IA3 dot dot dot.
Mhm.
So that's how you break A down. And B, what we're going to do is we're going to evolve that using this QDrift channel.
Mhm.
Um, and so if you've never heard about QDrift, it's a pretty simple idea. So with Trotter, we're doing each term in order, right, for a certain amount of time, and then we just loop back and we keep repeating this.
Mhm.
So with QDrift, what it says is instead of doing each term in order, you're going to make a probability distribution over your terms, and you're going to sample a term, and you're going to simulate that one, and you're going to do it for a fixed amount of time. Okay?
Mhm.
So, and then if you draw enough samples, that it tells you that the overall simulation channel, like this randomized channel, will be close enough to the ideal channel.
Mhm.
Does that make sense?
It makes sense. I guess the million-dollar question is how you construct the probability distribution such that you can just sample it and get the right result.
Yeah. So the probability distribution is incredibly simple. Uh, it's the spectral norm of that term divided by the sum of all the spectral norms. So it's kind of like an importance sampling.
Mhm.
But the idea being that the stronger your term is, the higher the probability that you have of simulating it.
Mhm.
Uh,
And
and
there are
s-
no, sorry.
no, go ahead.
So are there any unexpected consequences of sampling from that distribution and not maintaining some form of fixed order? Like, are we completely agnostic to the ordering in which we sample terms? So if we compare trotterization then to QDrift, trotterization has a clear ordering, and that ordering may be arbitrary if we just break it up. But is it perfectly arbitrary though? Like, can we? So if you imagine in trotterization um, that you would order all the terms such that you time evolve, like let's say you can break down A into A1 and A2, and then you would time evolve, you would order them such that you time evolve all A1s in sequence and then all A2s in sequence. I guess that would give you the wrong result. So the ordering in some sense is important, but we're saying then that the ordering, that sampling from the probability distribution sort of preserves the necessary ordering, if you will, or the, well, I think you see where I'm getting to. Preserves the important part of whatever this ordering conveys.
Yeah. So, no, that is a very good idea. Because what people have before this paper, what people had studied was, okay, like we have our trotter decomposition, say term one, term two, term three. Like our labeling of the terms is arbitrary. So we should really be studying like all possible permutations. We pick a permutation at random. And some people studied that and they showed that for I think second order, like first, second, and up to fourth order trotter, um, that this approach gave you about a factor of 10x reduction in the gate cost to reach a certain accuracy. Um, but that's about it. And they couldn't show any analytic results. It was all kind
Mhm.
of numerical and empirical. And some other people at Microsoft, they tried studying like this idea, like you said, what if you do all of your A1 terms first, then all of your B terms, or all of your A1, then all of your A2, right? So this is kind of moving across trotter steps. And what
Mhm.
they kind of studied was, well, what if you have like two trotter steps? You take all of your weak terms in that first trotter step and sort of just lump them into the second one. So you do all of your strong Hamiltonian terms from the first time step, all of your strong trotter steps from the second time step, and then you do all of the weak terms.
Mhm.
Uh, and again, they didn't really get any analytic results. They just kind of showed, hey, this seems to give about a factor of 10x improvement in gate cost if you're trying to meet a fixed error threshold.
Mhm.
So it's sort of the easiest way of thinking
Is
about
there some comparison to truncating those terms altogether? Could you do that as well? Like if you have some
it.
weak terms,
Yes.
just cutting them away, because I guess that would have a similar effect.
Yes. What people do is if you're trying to simulate to an error epsilon and your spectral norm has a spectral norm of a term is smaller than epsilon, you can just throw it away and kind of just take away from your error budget.
Mhm.
But the idea being that that's not a very, one of the ways to interpret this paper is we say that's not a very good idea. Instead, you should just randomly sample if you include that or not.
Mhm.
And just simply the fact that you could sample it kind of seems to increase the channel accuracy.
Okay, cool. So I think a follow-up question from my side would be, we have these two ways of approaching things, Trotterization and QDrift, and Trotterization has a higher gate cost in general, I suppose, or that's my understanding right now, but maybe they're just for very specific Hamiltonians where the gate cost is higher. And then the drawback of QDrift in isolation is accuracy, or is there something else?
Yes, accuracy is a drawback of QDrift. So the whole thing about Trotter is that you have to visit each of your terms in order, right?
Mhm.
Like if I have a Hamiltonian of 10 terms, I have to simulate all 10 terms, assuming you don't do this small term dropping off. All
Right.
right. So let's say they all meet some error threshold. Uh, so that means that your gate cost is going to scale like the number of terms. Now, the beauty of QDrift is that because you're just randomly picking which term to do, it doesn't depend directly on the number of terms.
Mhm.
And instead, it depends sort of on this normalization parameter. I mentioned that the probability of picking a term is its spectral norm divided by the sum of all the spectral norms. So QDrift scales with that denominator.
Okay. You want it to be, you want the distribution of that to be very sharp for it
Yes.
to
So you,
be accurate, or
yeah. So essentially,
or
the
scale,
worst case
right?
for
Sorry.
QDrift is each
Yeah.
term has the same spectral norm,
Hmm.
right? In that case, you're picking uniformly at random, and the QDrift scaling is going to go like the number of terms.
Yep.
The best case is whenever if you have like some exponentially falling off distribution, where say the strength of the first term is one, the strength of the second term is one half, then the third one is a fourth, and so on. It just keeps having at each step. And in that case, the QDrift is going to scale like the logarithm of the number of terms that you have.
Is that the best case scenario? So I would have naively expected that something like a delta distribution would be the best if you could get to that point.
Uh, Probably, um, but in that case, your the strength of each term is other of the other terms are zero. So in which case that just kind of tells you, hey, you don't know what you're trying to simulate.
Okay, okay, fine. Not exactly a delta, but like close to it. Like the more it pushes toward a delta distribution, the better.
Yeah.
Or is
At
that
least
not
in
the
terms of
case?
this parameter, you're 100% right.
Okay, okay.
Yeah. Um, so yeah, so that's how QDrift scales. It has this. Actually, if you, could you scroll down a little bit?
Yeah, sure.
Yeah, QDrift. Yeah, so you
Okay.
see equation 28.
Mm-hmm.
So that lambda factor, that's the sum of all the spectral norms.
Okay.
T is your simulation time, and E is your error that you're trying to approximate the ideal evolution with.
Mm-hmm.
And so now the error metric with this, right? Because you always have to ask like error with respect to what.
Mm-hmm.
So typical simulation, they want to show that the unitary that you construct that your circuit is, the
Yep.
difference between that unitary and the ideal unitary, which is just e to the IHT, for time independent. They show that that spectral norm is below some threshold.
Mm-hmm.
The problem is that only works for unitaries. And QDrift is not a unitary, it's a channel, right? Because how do you randomly apply? How do you analyze a randomly applied unitary? Um, you sort of have to use a different error metric.
Mm-hmm.
Uh, and that error metric that Campbell used and is used a lot in quantum information is just called the diamond norm. And there's like one other name for it, but diamond norm is what you'll typically see.
Okay.
And it essentially accounts for all possible, it tells you that the channels, the difference between them, will be close for all possible inputs, even if they're entangled with some other system.
Mm-hmm.
The idea being that if you just look at inputs over your input space, then this input could be entangled with something else, some other register.
Mm-hmm.
And you can show that if you don't include that entanglement, these isolated distances can be bad. Um, so
What
diamond
do we
norm
mean
accounts
exactly
for like
when we
all
say what do we mean exactly by that? So if we're not taking the entanglement into account, these distances, was the distances you use could be bad.
yeah, so you can imagine the spectral norm, right?
Mm-hmm.
It sort of just looks at your unitary or your channel acting on some input space, and you just maximize over all possible valid inputs of this input space.
Mm-hmm.
Now, the problem when you consider channels is that this input space can be entangled with something else.
Mm-hmm.
Uh, and so in reality, I forget which way it goes, but this entanglement can either give you a reduction in distance, like you can distinguish between two channels
Mm-hmm.
um, that you otherwise wouldn't be able to. Uh, yeah. Actually, sorry, that's the way you want to think about it. Is this
Okay.
discrimination problem? So
Mm-hmm.
you do know about the trace distance?
Well, enough to know, enough to recall the name, but I wouldn't be able to recite it.
Okay. Uh, so the trace distance, you should sort of think of it as just this. It tells you how much you can discriminate between two states.
Hmm.
Uh, if I give you, like, let's say I have two states, rho sigma, and we play a game where I give you either rho or I give you sigma, and you can do some measurement and you want to tell me which one I gave you.
Hmm.
Uh, if they're the same state, you shouldn't be able to just like you should have probability one half of guessing whichever one is right,
Hmm.
right? Because they are the same state, so you're gonna guess you have probability one half.
Yep.
If they are orthogonal, there is some measurement you could do where you could pick them out, right? Hey, you gave me rho. Hey, you
Hmm.
gave me sigma. Uh, and so as the trace distance goes to zero, this probability of winning this game goes to one, and as the trace distance
Okay.
goes to one, this probability goes to one half.
Hmm.
So small trace distance, high chance of winning. Low trace distance, bad chance of winning.
Okay. So high trace distance is just indicating orthogonal states, or
Yes.
is that a simplification of it, or is it really like that as well? Like a high trace distance is directly an indicator of how orthogonal the states are as well, or were we speaking in terms of an analogy just now?
It is some metric of orthogonality. It sort of
Okay.
says that the supports of the matrices are orthogonal,
Hmm. Okay.
um, if I remember right.
Hmm.
But yeah, so you want to think of the diamond distance as this kind of discrimination uh, probability, but for channels.
Okay.
So so that's like it's sort of like most natural way to, or it's the best kind of metric you can do for a channel.
Hmm.
Uh, and so that's why Earl Campbell, when he did QDrift, you have to analyze QDrift in terms of this diamond distance. And because we're using QDrift, we have to use this diamond distance for all of our stuff.
Right.
Uh,
Right. So also in a composite of the two approaches, you would use the diamond distance as your metric.
yep.
Okay. Cool.
Yeah. And just the key point, just the one takeaway is that it's inherently better than just using a spectral norm.
Hmm. In the case of channels.
Yeah.
Hmm.
Yeah. Because you can always extend, if you, that's one thing we do, is if you have a bound on the spectral norm between, say, Trotter and an ideal, we just can convert that to a bound on the channel distance.
Hmm.
But yeah, so I guess uh, m- the other interesting bit. So we talked about how QDrift has this lambda squared factor, but
Yep.
then its time in epsilon, like so it scales with t squared and 1 over epsilon.
Hmm.
That's not good. For Trotter, the first order has t squared over epsilon, but when you start symmetrizing it and going to these higher orders, you can get this t scaling to go like 1 t to the 1 plus something relating to its power.
Hmm.
So the higher up in order you go, the closer to 1 this exponent gets.
Okay.
But the problem is the higher up in order you go, the constant factors in front also just blow up, and they blow up exponentially.
Okay. And those constants represent a gate cost as well. They're a constant in the gate cost equation. Okay. So, right. You would still have in the asymptotic limit a benefit from it, but not necessarily in a concrete application.
Yeah, exactly.
Okay.
So in terms of
Hmm.
t, yeah, just go to the infinite order in terms of asymptotics of t. But in
Hmm.
terms of actually doing a channel, typically like second and fourth order is what people look at.
Okay.
Uh,
Is that also what you wanted then to get to, particularly with this paper? Like, so there are two sections of the paper, right? There's first this one on the first order, and then you have higher order, or I don't recall if it was higher order or just second order, but
it is higher order.
okay. And that's what you're where you expect this composite algorithm to perform at its best as well, is in that regime, or
Uh, yeah, so the case in which this composite approach works, it heavily depends on this ratio of t over epsilon.
okay.
Uh, So like another case of trotter, that error, the 1 over epsilon, it goes like epsilon to the 1 over the order. So
Hmm.
as your order goes up, this epsilon scaling goes to epsilon to the 0.
Hmm.
Um, but yeah, so the composite approach, it depends a lot on uh, it depends a lot on how you split your Hamiltonian up into the trotter part and into the QDrift part. And what we show is that if you can find parts to where this uh, the sum of the spectral norms in your trotter part dominates the overall sum of the spectral norms. Does that make sense?
That makes sense. Yeah.
Okay, you look a little confused.
Ah, sorry,
So
sorry.
yeah, so the sum of the spectral norms in this trotter part sort of dominates,
Hmm.
uh, and the commutator parts of the other bit tend to dominate the commutator cost. Then you can kind of win.
Okay.
Uh,
Why
and
is
so
it
this,
so? Yeah, that I was waiting for the kicker before. I guess that's the kicker. What does it mean then? So, I mean, if it wouldn't have said the second part, we just want it to be we want the spectral numbers to be dominated by the first part. That sounds a lot like we just want to use trotterization, period. But then we introduce this additional aspect of the commutators, and they should be dominated by the second part. Do you have? And maybe you were coming to this. Sorry if I'm interrupting you. What is the conceptual reason for wanting to have it with that split? Like, why is there that we have a an advantage of splitting it up in that way? I'm trying
mm,
to understand um, why this particular split. So is it?
I guess
I'm thinking in terms of the strengths and weaknesses that we were talking about before. That trotterization is the more accurate approach, and that QDrift is the more rapidly converging one. I guess we're getting back to that point, and somehow, but I don't see the connection between the split up that we're doing and the strengths versus weaknesses of these approaches. Are you able to tie those two together?
yeah. So I guess sort of the picture I kind of have in mind when thinking about when this composite approach works is when you have a few terms that are really strong and they all mostly commute with each other. And then you have a bunch of weak terms that we don't really know what their commutator structure really is. We know they're weak, and we
Mm-hmm.
know they also don't really have any, they kind of commute with the strong terms, but not really. The
Mm-hmm.
idea being if you were to do Trotter for this case, you would do your strong terms just fine. Um, Maybe you take advantage of this commutator structure and do them all kind of next to each other. But if you don't
Mm-hmm.
know that, then maybe they end up separated. But then you also have to do all these weak terms. And the downside of QDrift is you're essentially just going to be picking these strong terms the vast majority of
Mm-hmm.
the time. And so what this approach kind of allows you to do is say, okay, take advantage of that commutator structure of the strong terms and do them with Trotter, and then just randomly pick some of the small terms to do. So you kind of you don't have the accuracy loss if you were to just throw them away, but you're not going to have to pay the cost of doing each of them one by one.
Mm-hmm.
Uh, and then the other key point is that this works best at a specific ratio of t and epsilon.
Why is that?
And so yeah, the reason that is because if you go to like let's say you have a second order Trotter formula,
Mm-hmm.
its scaling with time is going to be like t to the 3/2, right? The scaling
Mm-hmm.
with qdrift is going to be t squared. If you go to long time, that t to the 3/2 is always going to win, like no matter what.
Mm-hmm.
This is for fixed epsilon. And no matter what these constant factor ratios are, there's always going to be some time where the trotter cost wins.
Mm-hmm.
Now, on the downside is if you imagine going to uh, small time, that t squared kind of starts winning, right? Because you can go to a time. low enough to where you have to do a single trotter step, right? You have to do at least one.
Hmm. Yeah.
Uh, so that means you have to visit all of your terms. Whereas QDrift can just sample maybe one term.
Hmm.
Uh, so as t goes to zero, that sort of tells you that QDrift is the right way to do it.
Hmm. So
And
t
now
goes to zero. Yeah, sorry.
I was going to say, and it's in this intermediate regime where you can kind of have this advantage of doing this composite approach.
Hmm. So the limit t goes to zero makes perfect sense to me. That it would be inefficient to go through the trotterization. Is there some similar conceptual understanding? So, like mathematically, I understand that the trotterization will win for large times.
Hmm.
Can we say something conceptually about why? So, Q-drift to me naively seems like something you that wouldn't inherently be worse for long time periods compared to trotterization. If we're just looking at them in isolation, what is it if you're comparing just Q-drift to trotterization in isolation that makes trotterization the better alternative for long times? I mean, conceptually, fine, the error scales with time squared. That's the reason. But if there is something more we can say about why that appears or why how to think about it.
Um, I can give you a slightly other picture. So you can think of QDrift as, say you have your state space, right? You have
Hmm.
your initial state, and you want to time evolve it, right? Which maybe you know that the exact time evolution state is somewhere over here.
Hmm.
With QDrift, what you're doing is you're randomly picking terms to do, right? So maybe with probability
Yep.
one half you go over here, probability one half you go over here. And then as you keep doing this branching part, after enough steps, you kind of have this blob of where you could end up.
Hmm.
But the idea being that the expectation value is going to be close.
Hmm.
So in as time goes, say very long, the problem is that this blob just keeps growing and growing and growing. And so the number of samples you have to do to reduce this blob to something reasonable, right? Because the more samples you do, the smaller this variance gets.
Hmm.
Uh, it doesn't really scale very well in this long time regime.
Hmm.
Whereas Trotter is, it's going to be this breakup part, like you do and it's going to guarantee that's somewhat close. I guess I'm trying to get it on camera,
Hmm.
uh, and it because it has this kind of distance scaling, it can go to long orders much easier because you can
Hmm.
kind of just control how close you are a bit better.
Okay. Hmm.
Whereas QDrift, it's just sort of this incoherent blob.
Right.
And so another case, if you're curious, that people have studied is, well, what happens if you fix your input state and you fix the observables that you're measuring, right? Because typically people don't want the exact state as a outcome of a simulation. They typically want to do something else, or they want to perform some measurements on the state,
Hmm.
right? Like if you're doing time dynamics, you want to say, okay, what's the probability of my electrons in the left half, or so on.
Yeah.
So you
Hmm.
have some observables you want to measure. And what
Right.
people have studied is, can we bound this Q drift blob if we fix the inputs and we fix the observables? And you can get improvements.
Okay,
I
but
don't know enough.
still not really competitive to trotterization over long time periods, or like are
Uh,
the improvements on the order of like really changing this gate cost that we see here from like t squared to something more reasonable, or is it still like I don't know window dressing improvements kind of thing?
I don't recall off the top of my head. I believe it was some kind of T improvements, but yeah,
Uh-huh.
I don't want to recall. I can't recall off the top of my head, and I don't want to misconstrue it.
Right. Okay, fine. So we have this intermediate regime where we potentially can get some benefits. What else is it that we ought to consider? So we want to be able to split up the Hamiltonian in a good way. We want the time over epsilon to be a good value. Is there something else to take into account?
Um, so I think that that's sort of the main gist is that this T
Hmm.
over epsilon has to be a certain decent value, or in this intermediate regime. And you want to have your spectral norms satisfy some uh, distribution, and you want the commutator structure has to kind of play nicely with you.
Hmm.
Uh, the whole point of this paper was just to kind of bound the cost and show that you can get an expression for the cost if you do this approach.
Hmm.
And the neat thing that we do is we also give you a way to choose this, what we call partitioning. Partitioning being term one should go into trotter or QDrift.
Hmm.
And the partitioning approach we did is again another level of randomization, where each term has some probability of ending up in trotter or QDrift.
Hmm.
And the neat thing that we show is for a specific Hamiltonian, uh, if your terms satisfy that falling off like one half,
Yeah.
where term one is strength one, term two is strength one half, and term I is strength one over two to the I. We show that if your spectral norms satisfy this and the commutator structure has some nice property, then this partitioning scheme will win in this intermediate regime.
Hmm.
And the way in which you win is that the cost of the composite is in little o of the minimum of QDrift or Trotter. So that means
And
sorry.
well, my follow-up question was going to be whether or not you have upper bounds for how much of a reduction in gate cost you could get, but that's kind of what you're saying already, no?
It means there is some L, some,
Yeah.
some number of terms
Uh-huh.
that you can get an arbitrary gate cost improvement.
Uh-huh. Okay.
It's always constant factor. It's not a T or over epsilon improvement, but it's just this constant factor.
Hmm. Okay.
And if you think about it, that's sort of the best you can do. If you're combining Trotter and Q-drift, you're not going to get magically better T scaling somehow.
Hmm. Yeah.
Um, but it does kind of show that a lot of this previous research, which was like say on randomizing the order or moving your terms across Trotter steps into like different
Hmm.
buckets, shows that like hey, like you can kind of do this a bit more systematically,
Hmm.
and the improvements you get from that are much better.
Are there any specific Hamiltonian? I mean, we talked about Hamiltonian structure that we want for this approach to be good compared to Trotterization and QDrift. Are there any like experimental setups or Hamiltonians that you think would be well suited for application with this kind of algorithm? Like, does
Yeah,
that map well onto some of the problems that we observe and where we think we can do well, where we can do better now?
yeah. So we did do some follow-up numerics. It's not in this paper, um,
Hmm.
but there's a paper by Matthew Pockernick. He's a grad student here. Myself, Nathan De Vera, and Juan Carrasquillo. Um, and we did essentially a numerics investigation. And
Yeah.
we also extended this approach from real-time simulation to imaginary time evolution.
Hmm.
So that's essentially thermal state preparation. Uh, the analytic results, it's not super important, but the numeric results, what we did study is we studied a Gellium model, which is like a uniform electron gas, which is
Hmm.
essentially where you just have a box with a bunch of electrons in it.
Yeah.
Uh, that model seemed to work pretty well. And we also studied hydrogen chains. So you just take, say, proton, proton, proton in some chain, and you simulate the electrons. And the improvements we got, so these are all kind of standard toy models for chemical simulations.
Right.
Uh, and the improvements we got ranged anywhere from 2 times reductions in gate costs compared to Trotter or QDrift, up to I think like 17x reduction.
Hmm.
So it depends a good amount. Um, and it also depends on the partitioning in which you do. So the other point of that paper was we studied the way in which you split it up, how does that impact the cost? And so we analyzed a couple different ways. One of them was we threw some machine learning algorithms at it, and it seemed to work pretty well. It was really
Uh,
costly though.
yeah.
Uh, the other approach, which was pretty simple and seemed to work pretty well, was you just pick a spectral norm and you say all terms with spectral norm greater than this go into Trotter.
Mhm.
All terms with spectral norm less than this go into QDrift. And then by tuning this, you can you can get up to I think like a it was what 5 or 10x improvement.
Okay. So we're starting to be short on time, but one follow-up question on that would be if you're making that partition, is that only applicable if you're using first order trotterization, or is that also applicable to higher order trotterization? The reason for me asking is my understanding from the paper is that when we're using first order trotterization, we can get away with a deterministic partitioning scheme, but if we're going to higher order ones for reasons not well known by me at this point, we have to move over to a probabilistic partitioning scheme. That was my understanding. Is that first of all, if that's correct or not, and then secondly, how the partitioning you just described fits into this picture.
Uh, I that is correct. That is what we do in the paper. As far as if there's any reason behind that, that's just what we were able to get to work.
Okay. Okay.
Uh,
Cool.
I don't know if there's any like deeper reason why, but yeah, essentially the probabilistic just becomes a little bit easier to analyze because now you're taking expectation values, and by parameterizing this probability distribution, you can tune those expectation values. So it's just a little bit nicer to analyze.
Mhm.
Uh, and the follow-up numerics, it uh, yeah, it kind of just verified that this simple approach seems to work in practice.
Mhm. Okay. Cool. For the last couple of minutes, the only additional thing I would ask is whether there's anything in the paper or any follow-up studies that you did that you think are just worth highlighting before we close this. Or also if there's anything like upcoming research that you think ought to be mentioned. Whatever you want with the last couple of minutes.
Yeah, for sure. As far as follow-up research on this, I there is so one of the interesting things about Trotter is it is one, it's the simplest simulation technique, and it somehow just keeps on kicking. Like a lot of these newer techniques of simulation, like qubitization, like LCU approaches and whatnot, they all have just better scaling asymptotically in terms of like t, in terms of epsilon. But because Trotter has this interesting commutator structure, there are known Hamiltonians where it outperforms even the best other simulation methods of like qubitization. And it's simply because of this commutator scaling. And so one follow-up approach of that you could do with this would be to say, could we extend that analytic or that regime where Trotter wins? Could we extend that to other Hamiltonians um, that take advantage of a different structure? I haven't done that. Um, Probably will not get around to it, but it is an interesting question, and I think it's probably worth exploring. The other interesting uh, bit is in this follow-up paper I mentioned that Matthew Pockernick did.
Mhm.
The analytic results of that, what they did was they showed you can extend this composite approach to imaginary time evolution, which is essentially preparing a thermal state.
Mhm.
And this is applicable to a lot of, it's known as quantum Monte Carlo. I don't know if you're familiar with that. But the idea
Heard it,
being,
but I haven't looked into it. Yeah.
okay, the idea being if like a chemist wants to prepare, say, the ground state of a molecule,
Mhm.
what they'll do is they'll kind of just do Trotter, but with these e to the minus beta h instead of e to the h.
Mhm.
So essentially break e to the minus beta h up into a bunch of e to the minus beta over k or something. Do a bunch of these small products, classically, on a classical computer,
Yep.
and then they do path integrals over each of these products.
Hmm.
And now, what this composite approach shows you is that, hey, uh, you can probably even do better on these classical computers if you don't do every single term and you do this, do some terms and then sample the rest.
Hmm.
Uh, and so that could even have improvements for classical techniques of how we find ground state energies.
Okay, cool.
Yep. And I guess
Very
that's about
good.
all I want to say.
Yeah, nice. We cut it exactly on time as well. So thank you very
Sweet.
much for giving the overview. I appreciate it.
Yeah, of course. I hope you learned something.